although the goal here is not to go with a lot of details in modeling electrical systems, but we're going to look at least some basics and some passive elements, okay? So based on our knowledge from digital circuits that you pass or electric circuits that you passed, there are two main laws that we will use. One of them is called the Kirchoff's current law or node law, and the other one is Kirchoff's voltage law or the loops law. Okay, so the node law says sum of all current going into a loop is equal to sum of all currents getting out of the loop. In other words, no electric current is generated or disappears through a node. The other thing it says also, sum of the voltages across a loop, if you consider appropriate signs, positive or negative, the sum of all these voltages is going to be equal to 0, okay? So this also comes from conservation of energy. So we use these two important laws, and then we have a ton of electrical equipment and elements, but we are going to only look at 3 of them right now, the passive elements: resistance, capacitor, and inductor. So if you remember, for a resistor, the voltage across the resistor is the constant of the resistor, we call it resistance, times the electric current passing through it, so V equal Ri. For a capacitor, basically, if you remember the laws for the capacitor, we said that the definition of capacitance is C equals Q over V, or delta V if you want to call it, where delta V is the voltage across the 2 plates of the capacitor and Q is the charge on any of the 2 plates, okay? And then the ratio, we call it capacitance. So if you do a cross product, you will get that Q equals C times V, or delta V. And now what you need is take a time derivative from this equation. And time derivative of electric charge is going to be electric current I, and the right hand side is going to be C dV over dt. Okay, so this is the law between the current passing through a capacitor and the voltage across the capacitor. I equals C dV over dt. Okay, so that's the governing law for a capacitor. And then also for an inductor, if you remember, the voltage across an inductor was delta V of an inductor was equal to L di over dt. In other words, the voltage generated across an inductor is basically proportional to its rate of change of electric current times a constant we call the inductance. Okay, so this is the law for a capacitor, this is the law for an inductor, and then for a resistor, if you remember, delta V was R times I, right? So these are the 3 governing rules for these 3 passive elements. Now we have a lot more elements, okay, like diodes, transistors, and so many more. But in this course, and for the scope of this course, we are not going to cover all of them. And if you go down here, I talked about, but they are for further studies, again, because the time of this course does not allow. But if you want to know about transistors and operational amplifiers or op-amps which use transistors, I have talked about them, how you can have different amplifiers, what are the relations, voltage, current relations in them. So all sorts of op-amps, whether they are there to take derivative of a signal, integrate a signal, multiply a signal, create lead, lag, and so many other things. So I mentioned them. and also fluid and thermal systems. Okay, so about non-compressible fluid, and then about thermal systems, I have mentioned some formulas and some examples, but the problem is many of these are beyond the scope of this course, and also, as far as I found, many of you have not completely passed thermodynamics, so you are currently in the course or currently in the fluid. Most of you, I guess, pass fluid, but not thermo, so I left them for now as a material for further study. If our time allows and we get some extra time at the end of this course, I might come back and talk about them. But for the moment, we're just looking at these three passive elements. So now, how do we model the behavior? How do we derive the governing equations, differential equations of an electric circuit? Let's say here, this is example 835, which is asking you to find the transfer function of output voltage over input voltage, EO over EI of S, for this circuit, which has two capacitors and two resistors, and do it one time using basically governing differential equations, and the other time using a method called equivalent impedance. So the equivalent impedance is just makes finding these transfer functions one step shorter or faster, and all it does, it takes the Laplace of the current voltage relation for these three elements, and we directly treat all three of them as a resistor. So what do I mean? So here, if I take a Laplace from the governing equation of a resistor, you see that V of S is equal to R times I of S, assuming that R is constant. So the resistance here is defined as what? V over I, of course, right? Now, if I apply the same thing to an inductor, what do I get? So I'm applying a Laplace transform. I would get V of S is equal to Ls I of S, assuming that, again, the initial condition is I'm looking into a transfer function. So here, if you divide V by I and treat it as if this is a resistor, okay, so it's not a resistor, it's an inductor, but if you treat the inductor as if it's a resistor, then the ratio of voltage to the current, which we call it what? We call it resistance. Here, it is going to be L times S. And we say this is the resistance of what? If I made this inductor equivalent to a resistor, this is the equivalent resistance. So I say this one and this one are what? Equivalent. But since it's not actually a resistor, it's an inductor, this guy, I'm not going to call it resistance, I'm going to call it what? Z, or impedance. Okay, so impedance is like a general resistance, a generalized resistance. Here, if I do it, apply a Laplace, it is going to be I of S is equal to CS V of S. And if you calculate again V over I, assuming that you're treating it as a resistor, this ratio should be the resistance. But if you do it here, it's going to be 1 over CS. Okay, so this is the equivalent resistance for a capacitor. Again, I call this an impedance for the capacitor. So the impedance for a capacitor, or the equivalent resistance, is 1 over CS. For an inductor, it's L times S, and for the resistance is, of course, just the resistance. It's the resistor, it's just the resistance R. So it's a generalized, as I said, resistance method. We call it impedance, and we show it by Z. And I said for a resistor, for a capacitor, and for an inductor, how we can calculate it, right? Now, what's good about it? I'll show you. when I want to analyze the circuit and find this transfer function, I'll show you how the impedance equivalent can make my life a little bit faster and easier. So let's take the circuit and then find the transfer function. So here is the circuit, and again remember that the goal here is to find EO of S over EI of S. So first we go according to what we learned from digital circuits or electric circuits, Kirchoff's current law, Kirchoff's voltage law, and then the governing equations for a capacitor and a resistor. So here I would call this current going here through this branch, I would call it I1, and I call this current here, I would call it I2, right? Then this I1 comes to another node, so I would call this basically, and this one, so if I call this I3, now what is this one? I can call it I4, but pay attention that this I2 that comes and passes through the capacitor C2 and comes back here, you're putting a voltmeter, right? You're measuring the output voltage. And when you have a voltmeter, the resistance of a voltmeter is infinite or very large. So it kind of like here, the circuit is what? Basically, the circuit is open, right? So here on this side, it is like you have a battery with the voltage of EI, but here you are having a voltmeter which literally makes this like a short circuit. So when it's a short circuit, there is no current passing through the voltmeter. So this I here, this one, this I is equal to 0. No current passing through it because it has infinite resistance. Therefore, when you come to this node here, I2 is coming into the node. One current I is getting out, which is 0, and another current is going this way. Now, clearly, sum of the current in is equal to the sum of current out, but since these two currents are out, that one is in and this is 0, so that guy has to be the same as what? This one has to be the same as I2, okay? Because this one does not go out, so I2 comes in, I2 goes out. Right, so this one here, this one, I can basically draw it backwards instead of this way. I can draw it this way. And clearly this is the same as what? I2. So it's not a new variable, I4. So I1 here comes in, I2 comes in, and I3 goes out. So one of the important things is do not create a new variable if it's not needed, because then you have to come up with another equation to eliminate it. Okay, so now I have 3 loops here. As you can see, there is one loop here, there is one loop here, and there is one loop here. And I have a bunch of nodes. One node is here, and one node is here. This node here already we take care of it by saying these two are I2. So it's not going to give us anything new. So now let's write down the equations for Kirchoff current law and voltage law. So if you do that, in this node here, I have what? Some I is going in and some I's are coming out. So clearly, what is this I that is coming in? Because this is I1 and I2 going out. So what is this current? This one that is going through the voltage source. What is this? Clearly, if you call this current I3, as I said, this I through this part here, this is I, and that I is 0. So when I3 comes down here and 0 is added to it, what goes out? I3. So this current that goes here in is I3 goes in, and then I1 and I2 are getting out. So that will be the same as this node. So you see they are very similar to each other. So I am going to just use one of these nodes, not two of them. And I would simply say I1 plus I2 is equal to what? I3. Some of the nodes go in is the same as node go out, or here vice versa. I3 goes in, I1 and I2 goes out. So the only node equation or current equation I get is I1 plus I2 is equal to I3. That's the only thing I have from the Kirchoff's node law. Then I have 3 loops, right? So this is the node. If I give them a name, so I call this loop 1, call this loop 2, and I call this loop 3. So for loop 1, what do I have? So I write it here for you. Loop 1, I'm writing the loop law. What does it say? Well, EI, here this is positive, negative. I'm passing through the voltage, so it is going to be positive EI. I'm passing through a resistor in the same direction as the current. When you pass any element, and I guess I mentioned it somewhere, hopefully. Let's see. Well, I'm not sure here I did that, but if you know it from your electric circuits, if you pass any passive elements in the direction of the electric current, the voltage drops, and vice versa, which means if you pass it in the opposite direction of the current, the voltage increases, right? So if you want, you can add that as well. I just want to make sure again my notes are complete. So if you pass it in the opposite direction of the electric current, the voltage increases. If you pass a power supply from the negative end to the positive end, the voltage increases. And if you pass it from the, and if you go through it from the positive end to negative end, the voltage drops. Okay, so again, I want to make sure that you remember what you guys had in your circuits course, and we're going to apply them right here. So if you look in loop 1, I'm passing the voltage source from negative to positive, so the voltage increases. Then I'm passing the resistor R in the direction of I1, so the voltage drops. Then I'm passing capacitor C1 again in the direction of I3, so the voltage drops. And the voltage across that is integral of I3 dt, which is Q, correct, divided by C1. And then since I go back to the same place, sum of this is equal to 0. Then we go to loop 2. Okay, and loop 2, you can write what? So you start from any point you want, let's say this corner. Now you are passing opposite to I3 from C1, so the voltage goes up. So you will get positive of integral of I3 dt divided by C1. And then you are passing this resistance in opposite of I2, so it is going to be positive Ri2. And then minus VO is equal to 0. And again, because this VO has its positive here and negative here, so you're going from positive to negative, so the voltage drops. Okay, so that's loop number 2. Then you can have loop number 3. For loop number 3, again, you start anywhere you want, let's say here, and you pass C2 with I2 in the positive direction, and then this R in the direction of I2, that R in the negative direction of I1. So it is going to be negative integral of I2 dt over C2 minus Ri2 plus Ri1 is equal to 0. Okay, and so now you have 4 equations, and I always recommend you number your equations so that you don't get lost. And so the goal here is to find VO versus, or EO versus EI. Okay, so this one I can call it VEO instead of EO. So if I can find one versus the other, then from that equation I can find basically the ratio of the two. So as you can see, there are some parameters here that I need to get rid of. Like what? Like I1, I2, and I3. These are unknowns, and I do not need them, and they appear in most of my equations. So I have 4 equations and 3 parameters to go. If I can eliminate these 3 among these 4 equations, I'm down to 1 equation between EI and EO from which I can find the ratio, which is the transfer function. Okay, so now I need to start applying Laplace transform. So I apply Laplace to all of these equations, and then I will get I1 plus I2 is equal to I3. I'm not going to write I1 of S, I2 of S, because that takes a lot of time. So you know, when I write them as capital, they're all functions of S. So EI is equal to, and I take the negative terms to the other side. So EI, it is going to be RI1 plus 1 over C1S I3. Then we have EO is equal to, I take EO to the right hand side, it's going to be RI2, and then plus 1 over C1S I3. And then finally here, if I take the negative terms to that side, I would get RI1 is equal to RI2 plus 1 over C2S I2. Okay, so I get these equations. Now, if I did the impedance method, the impedance method directly will bring me here. The impedance method will directly bring me here. Why? Because in the impedance method, this is what I do. I replace the capacitors with an equivalent what? Resistance. So I say, this is a resistance R. This is another resistance R. This is a resistance, but its resistance is what? 1 over C1S, the equivalent impedance. And then here, this is another resistance. And that guy is 1 over C2S. And so then I had basically, here was I3, here was I, and since everything is in Laplace domain, I can just use cap I3, and this is cap I1, and this is cap I2. So if I wrote my equations, I would get my node equation here. For this node, I had this equation. Then for the first loop, you see EI is RI1, and then if you remember, this guy was I2, and this one was I3. So I'm passing in the direction of current, so negative RI1, negative I3 times 1 over CS is equal to EI, as you can see. Then in this one, EO is going to be equal to, since I'm passing these two opposite of the direction, so it's going to be positive 1 over C1SI3 positive RI2 minus EO is 0. So if you take EO, you're going to get this one. And here again, it is going to be negative 1 over C2SI2 because I'm passing in the direction of current, minus RI2 plus RI1 is equal to 0, from which I get this bottom equation. So the impedance method is basically like, I still write the equations for node and voltage, but they are already taken Laplace. I already have taken Laplace from them. Okay, so the Laplace is already applied. So it gives me these equations instead of these ones first and then applying Laplace. I directly come to here with the impedance method. Okay, so it saves my time. Now here, everything is linear, okay? You treat this 1 over C2S as just a constant like R1 or R2 or whatever. So you treat these impedances as constant, and then you solve for what? EO versus EI. I and get rid of I1, I2, and I3. So clearly, wherever you see I3 from this equation 1, you can plug I3 in 2 and 3 and plug it with 1 plus 2, correct? So if you do that, I plug 1 here and here, and that makes my equations a little simpler, right? So 1 in 2, 1 in 3, right? And you leave 4 as is. So it is going to be EI is RI1 plus 1 over C1S times I1 plus I2. Then EO is RI2 plus 1 over C1S I1 plus I2. And then simply RI2 is equal, and here I factor out I2, it's going to be R2 times R plus 1 over C2S. Okay. And now I can eliminate I1 or I2 in these guys. So let's say I eliminate one of them, it doesn't matter. So from here, actually I can divide this by an R and set it equal to I1, right? Because that's what it is. So I call this now equation 5, 6, and 7. And now if I plug in 7 into 5 and 6, I1 goes away, right? So that's what I do. I plug in 7 in 5 and then 7 in 6. So I will get EI to be equal to, so it's R plus 1 over C1S times I1. But I1 is already calculated based on I2, so it is going to be times R plus 1 over C2S, the whole thing over R times I2, and then plus 1 over CSI2. And then EO will be 1 over C1S times I1, and then plus R plus 1 over C1S I2. And this is that same thing on the top. So if you factor it out, this is going to be I2 times some big thing, right? And that big thing, it is going to be C1, C2S, and then times R. And then here, it is going to be 1 plus so it is going to be C2 going to be R C1 C2S plus C2 times R C1 C2S plus C1, and then plus 1 over C1s. And this is going to be I2 times R C1 C2 S squared, and then 1 plus R C2 S, the whole thing plus C1s over RC1s plus 1. Okay, and then if I call them basically 8 and 9, I can divide, because 9 is EO, that is E8, so all I need is now divide 9 by 8. If I do so, now I would get EO of S over EI of S. It's going to be, the I2s would be eliminated. It's going to be the ratio of these two brackets. So this bracket is going to be this guy. If you take common denominator, the top one is going to be you have to multiply. So it is going to be R squared, C1 squared, C2 squared, S squared, plus C1, C2, plus some of those guys. So this is going to be RC1 squared, C2, that's RC1, C2 squared. And then plus RC2. Okay, so this is going to be this one. And this, I bet you can make it simpler. Okay, so just cross out this with that, and S term remains, which multiplied by this whole thing. So you will get R squared C1 C2 S squared plus 2R C2 S plus 1 divided by R squared C1 C2 S cubed. These are squared also. Then plus R C1 C2 times C1 plus C2. This whole thing times S squared. Then plus something times S. And that something is C2 times R plus C1 times C2. Okay, so you're going to get something like that. Okay, a third order system if I have not made any calculation mistake. So again, the answer, whether you do impedance or not, it's just the same, just the impedance just reduces one step, but other than that, the final answer should be the same.